Good afternoon. I'm here to talk to you about a proactive solution to improving longitudinal joint performance. VRAM. So what is VRAM? VRAM is a thick application of hot applied polymer modified asphalt. This is not an emulsion. You can sample test this out of the spray bar, and VRAM will true grade out to an 88 minus 28, but there are some additional properties added to it. Depending what state you're in, the product is also referenced as LJS, Longitudinal Joint Sealant, or of course the VRAM, Void Reducing Asphalt Membrane. Our VRAM/LJS is J-band. So why do we need J-band? This is an actual sign from our signs from outside the city of Chicago, warning drivers to avoid lane transfers or switching lanes because of potholes. Here's a picture a little closer to home. This is on the PA Turnpike. As you can see, joint failure starting there on the shoulder and on the center line joint. So why do joints fail early? This is a study from Washington State DOT on the effects of in-place voids on the service life. So if you look on the left-hand side there, mix designed at 7% air voids is going to give you 100% service life. As you get away from that center of the mat and out towards the unconfined edge or the joint, you're typically around 10 or 11% air voids, and you can see your service life goes down to about 62%. Here they're looking at center line going in towards the interior of the mat to see how far that large area of voids last. So again, if you look at left side would be your center line where you have 11% voids. And as you go in there till you get to your 7% design voids, you're at 9 inches. So you have the 9-inch area there that's a problem. So then they wanted to look at the effects on the pavement life with the air voids. Again, at 7% air voids designed for a 15-year life. As you get towards that unconfined edge or the center line joint, where you have the 11% air voids, you're down to 10-year service life. So you lost 5 years out of your pavement. The issues with the longitudinal joints: you cannot achieve the same density at the joint as in the mat, and water, which causes water and air intrusion, accelerates the damage. And as most of us know, the longitudinal joints commonly the first area requiring maintenance on a pavement job. So over the years, we as an industry have come up with or tried to find some solutions to this, methods to improve the joint. One is joint density spec. And typically they target air voids at 4 inches from the joint, not exactly on the joint, with 2% of the centerline mat voids. Echelon paving that eliminates the joint. Notch wedge, of course, is shown in the picture. Cut off the lower density unconfined edge, or using the pizza cutter or mill and inlay. All the above are mechanical solutions, and although they help with some improvement, haven't solved the issue. So in early 2000, Illinois DOT recognized the need for better joint performance. Their failure mechanism was permeability, and the concept they came up with is fill a portion of the voids with asphalt, with an asphalt product from the bottom up. And that's where the Void Reducing Asphalt Membrane, or VRAM, came from. So it's applied, you apply a heavy band of polymer modified asphalt out of the distributor. Of course, the nozzles and spray bar can, a little different configuration there. It's sprayed 18 inches wide, as we talked in the previous slide, that our trouble area is 9 inches from the unconfined edge in. So you're going to pave half of that with the first pass. Second pass will cover the other half. The heat and the migration, or the heat and the compaction from the rollers, will help the material migrate up through. So here's how we figure out the application rate. So if you have an HMA at 5.5% AC at 1.5 inches thick, you're looking at 9 pounds per square yard of AC. So the VRAM for this application rate would be 1.47 pounds per foot over that 18 inches, equates to another 8.8 pounds of AC per square yard. So total AC in the HMA and VRAM is 10.3%, again, in that 18-inch area. For a 10 to 13% air void mix at the joiner, the VRAM would occupy 2/3 of that overlay height. So there were 9 IDOT VRAM experimental test projects in 2002 and 2003. In 2017, they went back and took cores from 3 of these projects, US 51, US 50, and Illinois 26. This is just a couple of pictures. This is Illinois 50. As you can see on the left-hand side there, the J-band or the VRAM section has a crack up the center line, but really no failure. The control section there, you can see it's been patched because it was failed. Again, Illinois 26, VRAM section there on the left-hand side, crack up the center line, but as you look at the control sections without VRAM in the center and the right there, you can see the water got down through the center line joint and caused failure not only at the center line joint, but everything around it. So when they pulled these cores, they wanted to do some testing. And one of the tests they ran was the Illinois Flexibility Index Test, or IFIT. And basically this is testing the cracking resistance of the material. So they'll take the core, saw cut it in half, place it on the machine there, and they apply pressure till it cracks. And they actually come up with an FI number, so flexibility index number. For new paving, Illinois requires an 8 for passing. And now again, they're looking at 14, 15-year-old pavings here. So what they found is in the US 51 job, the VRAM J-band scored a 22 on the FI. Again, a new paving would be at 8. The control section without VRAM was at 0.1 less than, or 0.8 less than 1. The Illinois 26 project, again, with the VRAM in it, was a 9, again, 8 being great for new. And then the section or the control section was 0.2, virtually 0. So IDOT, after getting all their information together and all their data from 15 years plus of studies on the VRAM, put together a paper, submitted it to Transportation Research Board, and TRB just put that out in January of 2021. So it's published. And basically what they found in that, they stated that many approaches to improve the performance of asphalt pavement longitudinal joints have been tried by various agencies with mixed or marginal successes. And they're talking about the mechanical solutions there. And then they go on to say IDOT looked at a bottom-up material approach to seal the voids in the lower density longitudinal joint area, with the results being lower permeability and an improvement in predicted laboratory flexibility and field performance. Along with that, the high polymer LJS material has rut resistant and crack resistant binder properties that has easily been embedded into the construction process of the surface courses. And what they're seeing is a life extension of the joint area is approximately 3 to 5 years. And the benefit of that is calculated to be 3 to 5 times the initial cost. So that's what they wanted to go back to and look how this benefits as a cost. And to better understand that, they went back and they used net present values with sections with the LJS and sections without the LJS. And then they would minus out the LJS cost. Taking that value and dividing it by 5280 or a mile gives the cost benefit of this construction practice in similar units to the average awarded price of $239. So that orange line going across that chart there is their average price that they've been seeing for the VRAM LJS of $239. This was initially completed for a 20-year analysis, but was repeated for 16, 17, and 18-year analysis to better understand the progression, and the benefit of this construction practice is 3 to 5 times the cost of the material. So what they're seeing is that in the chart there, that 1 is your 16, 2, 17, 3, 18, 4, 19, 5, 20. they're seeing the extension of their life of roads because water and air isn't getting into their joints and destroying not only the joints, but the mat. They're able to get 17, 18, 19 years out of it. And if you look at 18 years, that's 3 times their initial investment. So VRAM, J-band a little closer to home here. In 2018, PennDOT did 2 test projects, SR81 and SR380. These were both SMA mixes. Both projects were paved by the same contractor and the material came out of the same asphalt plant. In 2019, we went back to revisit the site just to do a visual. As you can see on the left-hand side there, the J-band joint looks very good. The right-hand side is the control joint, and you can see the control joint started to open up. It's about 1/4 of an inch there. Again, 2019, another picture of that VRAM joint. So with COVID, we weren't able to do our 16-month review. So we went back in July of 2020, which was actually 21 months. Again, on the left-hand side, you can see the VRAM joint still looks very, very good. The control joint on the right-hand side is now open about 1/2 inch. There's a close-up of the VRAM joint. Here they are side by side again, but in reverse. The left-hand side is the control section with no VRAM, and the right-hand side is the VRAM. So this year on 2021, we'll go back to close this job out. It was a 3-year view on it, and I'm sure at this point they're going to have to do some major repairs on the control section. The VRAM section still looks great. So here's another VRAM project on the New Jersey Turnpike. The New Jersey Turnpike, due to the amount of traffic on it, requires mill and fill in their process. So they have to mill out, clean, tack, VRAM, pave, stripe, everything else in a 9-hour period. So we actually spray the VRAM at 9 inches here. The next night when we went out, milled the adjacent lane, then they would spray the additional 9 inches, turn one of the nozzles up to hit that vertical face from the previous night. This is just showing calibrating the VRAM. They'll spray across that 3-foot piece of construction paper, cool it off, fold it up, put it on the scale they have on the back of the truck, and make sure it's the proper rate. Here you see it with the VRAM down in the tack coat afterwards, the paving. Along with the IFIT testing, they also wanted to do testing to see the migration rate of the VRAM up through the asphalt. So you take a 6-inch core, freeze it, do a couple of saw cuts, and then they test the migration by the digital image analysis, or DIA. Basically what you're doing is taking a 20 megapixel camera along with the ImageJ software that can be downloaded from the internet, and you're taking 5 pictures at 5 millimeter increments to see the gray levels. And it's looking for pixel intensity, the contrast between the aggregate and asphalt. This will allow you to tell how far the VRAM migrates up. And this was developed by IDOT, Brian Hill at IDOT. So this just shows you the process being taken with a picture there, that 5 millimeter increments, the information sent back to the software that graphs it out. This is one of the actual cores or analysis cores from New Jersey Turnpike. This is a control core where you can see it's pretty much a vertical line, which means there's no contrast. There's no additional asphalt in there, no additional shading. Here is one of the VRAM cores from the New Jersey Turnpike. As you can see there was some contrast, migration up to 30 millimeters, or 47%. We ended up averaging about 52% on this job. So again, they wanted to do the IFIT test on this. They took the control core, the VRAM cores, and as you can see, if you remember, the IFIT number for new paving was 8. So the control core was good, it was a 19, but then when you look at the VRAM core, it's a 437. So that resistance to cracking and fatigue is going to be huge in that area. And I'm assuming we're going to see that very quickly. Again, it's sprayed hot applied polymer modified asphalt, sprayed at 18 inches wide. Vehicles are able to cross once it hits 130 degrees Fahrenheit. We tell the vehicles they don't drive down it, cross it. Guideline to be placed for the applicator and the paving crew. This is just showing at 18 inches wide, sprayed, non-tracking in less than 30 minutes, and everything we've seen is less than 10 minutes. First pass covering half the VRAM. Again, there's a sample spout on the spray bar. You can take a quart can, take it back to your binder lab, test it like you would a regular binder, and it'll meet that 88 minus 28. General application rate, again, based on your mixes. Here shows the states that have VRAM so far, again, started in the Midwest. On the east here, we have done South Carolina, Virginia, DC, Maryland, Delaware, New Jersey, and PA over the last 3 years. VRAM starting to be used heavily under the rumble strips, especially centerline rumble strips, to prevent early failure there, since you are milling them open, exposing them to water and air. And then the big thing, cost comparison, we talked about the benefit being 3 to 5 times your initial cost in one of the previous slides, but this also shows you your initial cost or your additional costs that you'll have as you go back out and maintain this project over the years. Your inlays, $8 a lineal foot, microsurfacing, $4.81 a lineal foot, route and seal, $2 a lineal foot, and here we have VRAM at $2.50 a lineal foot at construction. And these numbers came up. Illinois DOT came up with these numbers when they were doing their cost comparison. So in summary, the application rate's based on volumetric, so it's tailored to your specific mix, provides a material solution, reducing the air voids at the longitudinal joint, thereby reducing air and water permeability. Multiple field projects in the last 15 years demonstrate improved long-term joint performance, may remove the need for echelon paving, reduces the need for joint maintenance, and increases the life of your pavement. Increasing joint life reduces the need for maintenance, improving safety for construction workers and the motoring public. And here I'll just show you a quick video just to show you the ease of using the VRAM. And this is from our project down in Maryland, paved last summer. Just an overlay, no mill or anything in front of it, basically tack and overlay. So just showing you the nozzles there again, they're a little closer than normal, so we can get this heavy application rate. Temperature of the product there about 325, 330. That's the important part, the layout, so that they know exactly where the center line is, so that they're hitting 9 inches on each side. And he's just getting his bar ready, and they're off just like a distributor. They're going 2 to 3 miles per hour, checking their width at 18 inches, making sure it's not flowing over, just a temperature check. You can see it's a little tacky, but it's already, trucks are driving across it. Here you'll see them drive across the construction paper so that they can calibrate their weight. They'll weigh that. Again, they'll cool it, weigh it, put it on a scale, 1.26. Matches up exactly with what their rate was supposed to be. Again, this job, it was 7 minutes till our VRAM product cooled so the traffic could cross it, and it was ready for paving. And then the paving crew is status quo with their paving. Nothing changes there. They're covering half the pass. Going down through. They actually had to wait longer for the tack to break on this project than for our product to cool off for traffic. So that's just the paving process there. And then I'm open for questions. My contact information is there. We have our website that you can visit, www.thejointsolution.com. Again, my email and phone number are below. And thank you for allowing me to present this product, and open for any questions.